Hey, this is Harry, and this is Physics 2 Lab 3, Magnetic Field of a Bar Magnet. Introduction. In this experiment, I measured and modeled the magnetic field of a bar magnet, as well as explored the relationship between distance and the strength of magnetic fields using a magnetometer and a computer model. I also calculated the magnetic dipole moment of the magnet. Some key concepts in this lab are magnetic fields, the Biot-Savart law, distance dependence for magnetic fields, the influence of Earth's magnetic field, and the magnetic fields of dipoles on and off axis. Here's some equations that we'll be using. Initializations. I align my phone with the Earth's north to south axis, my bar magnet with the east and west axis so they're orthogonal. This helps so that I can measure the magnetic field of the bar magnet separately from the Earth's. I ignore the Z component since it doesn't change that much. Then marked where the absolute value of X is at its maximum and Y is at its minimum, and vice versa, to find where exactly the magnetometer was located on my phone. Experimental data. I measure the distances for multiple magnetic field values to determine N from the equation for distance dependence. The log of both sides of this dependence equation is taken to get a plot with a straight line with a slope N and intercept ln k. N on the graph of ln bx versus ln r is negative 3.06. Mu, the magnetic dipole moment, is 2.1 am squared. For the off-axis values of the magnetic field, the y component of b net were adjusted for Earth's magnetic field by subtracting it from the measured y component. Here's my data right here. Calculations. To solve for mu, I first need to get k from ln k. And this is how I did it. Just use the Biot-Savart law, and I equated it to the distance dependence equation, rearranged to solve for mu, and I substituted in the known values to get mu. So here's my computational model. I'll just share it. So I substituted in the values from my experimental data into this code. I had to define the function dipole b, uses this Biot-Savart law. This is b scale so I can see the arrows. It's the distance. I define the vectors or the observation locations at different points for the on axis and perpendicular to the axis. I created the arrows for the magnetic fields on axis and perpendicular to the axis from each of the observation locations. And yeah, lastly, I made an arrow to represent the magnetic field 45 degrees from the axis. And this is how it looks. So it calculates all those magnetic fields. Comparison. At a distance of about 2.239 meters, the net magnetic field was this for experimental and this for computational model. As you can see, these values are pretty different. It's probably because I had issues with aligning my phone at the bar magnet. Lastly is the discussion. If I had done that instead, the measures of the magnetic field on and off axis would then be influenced by the Earth's magnetic field, which would in turn change the distances I measured. For the second one, if I did, the system of two magnets could be still modeled as a dipole since the ends touching would cancel out. Then in my data, the new system at the same values for the magnetic field would double the original distances, keeping the same direction. And that's it.